And greetings again. This is going to be instant premiered. You're watching it probably now as the instant premiere. And it's in conjunction with somebody who requested me to do some of the problems from their recent competition called the Fancy Backwards 3 Mathematics Competition. What? Oh, it's Sigma. I thought it... Okay. Anyhow, it was held this month, right now. Actually, it's probably happening right now as I'm filming this. And this is problem 1 from that competition. It was put out by PyCalc, and then there's an X, but it could be the Greek letter chi. I don't know, because I haven't heard it pronounced out loud. It's the PyCalc X organization, and I believe they are located in India. I'm not 100% sure on that. You can find out more from my previous video, which will have them linked, and also this one. I will link to their website here in this video as well. I'm only going to have time to do about 5 or 6 problems. We'll see how it goes. I got like busy 48 hours ahead, so we'll get what we can done. Welcome to the premiere if you're watching, and let's get started. A chicken lays either 0 eggs or 1 egg each day for 10 days in a row. If the chicken could have laid the same amount of eggs in exactly 120 different ways, what is the least amount of eggs it could have laid? Okay, by the way, the approximate difficulty of the competition is between AMC and Amy, according to what I last heard. And so, how is this going to work? It's basically a sequence of zeros and ones, and there's only zeros and ones, and there's no other options. So we want to know the least amount of eggs it could have laid, and there's basically 10 spaces, right? And in those 10 spaces is either a 0 or a 1. So you're looking for 10 choose the number of eggs laid to be equal to 120, right? Because you're going to choose where those eggs go in which slots. That's what it means by the same amount of eggs in exactly 120 different ways. So, most people don't know, like, the 10th row from the top of Pascal's triangle. So, yeah, I probably don't either. Let's just guess and check this. You're going to have 10 choose 4 is 10 factorial. And then over 6 factorial, 4 factorial. And that's going to be 10 times 9 times 8 times 7 over 4 times 2 times 3. I split the 4 and the 2 and the 3 up from 4 factorial, and I don't put the 1 because why? And then 4 times 2 cancels 8 and 3 cancels here, but you can clearly see this is not going to be 120. It's a little bit over that, which means it's probably 10 choose 3. In fact, after you've done one combination in any problem, you should kind of streamline the process. You can see that the 7 factorial is going to cancel. And so you can just write 10 times 9 times 8 over 3 factorial, which you can write as 3 times 2. And so if I cancel the 3 here, and you're going to get 3 here and 2 here and make 4, and 4 times 3 times 10 is 120. So the answer is going to be 3. There were 3 eggs laid as the least it could have been. You don't have to worry about 10 choose 2 because it's not going to stay the same there. Yeah. That's it for this one, guys. On to the next problem. All right, continuing on. This is problem 2 from the Sigma Mathematics competition. So, S equals this set of numbers, n to n plus 9. It looks like they're consecutive. That'll be important. Where n is an integer. 2 of the integers in S, which ones, we don't know, are multiplied by 10. If the sum of all these integers is now 100, meaning after the multiplication by 10, what is the greatest possible value of the sum of the original elements in S? Now, there's a couple ways you can approach this. The first way is you can do some algebra and then use reasoning to attack it. The other way is my brain likes to work at the lowest level required to get the problem correct. I feel like that stresses me out less, and I can save the concern and stress for future problems that are more difficult. And so what I would probably do with this is just try something out. Like, let's just say I took from 3 to, there's 10 numbers here because you're going n plus 0 to 9, and from 0 to 9 is 10. 10 digits, essentially. And so if I do 3, 4, 5, and I go all the way to 12, right, and I was to add these numbers, I would get 5 sets of 15 using the Gaussian method. That would be a sum of 75. Okay, as I started with that. Now, if I took the two smallest numbers and I multiplied them times 10, how much am I gaining? Yeah, I mean, there become 30 and 40 for those two numbers, but that's not what you're gaining. What you're gaining is 9 times 3 plus 4, right? Because you have to subtract the original 3 and the original 4, so you really have 9 times 7. You would need to add 63 to this, even if you took just the two smallest numbers. I mean, you can already see it gets to 100. We know the sum of the numbers from 1 to 10, for instance, is 55. Okay, so we can't get too far. You're already at 75 from 3 to 12. We know it's a low-level set of 10 consecutive numbers to work with. So the next thing would be, it can't be from 3 to 12. It's got to be lower than that. Let's try 2 to 11. From 2 to 11, 2 plus 11 is 13. 5 sets of 13 is 65. Even if I took the 2 and the 3, the two smallest numbers in the set, and I multiplied them by 10, thereby producing 20 and 30, again, it's 9 times, because you're subtracting the 2 and subtracting the 3, right? So in other words, what am I doing? I already had included in the 65 plus 2 plus 3. Now, when I put plus 20 in place of the 2 and the 3, I have to subtract those values from this gain because they're no longer there. It would be 20, 30, 4, 5, and so on. So I lost the 2 and the 3. So I didn't really gain a full amount of 10. I gained only 9 times that number, and 9 times the sum of 2 and 3 is 45. So the 45, again, is too big. But that makes me think, if I put that 45 with that 55, we're there. So it's going to be the sum of the numbers from 1 to 10, and the two numbers that you would multiply is the 2 and the 3, and you're going to get that the original sum is 55. In fact, 2 to 11 is too big as is. That forces it to be 1 to 10. It could have been lower than that, I suppose. But we want the greatest possible values. You can definitely do it with 1 to 10. If there was some lower number that allowed it, this is still the best option. So that's one way you can do it. That's the way that I did it when I was solving it. But you should always be second guessing your approach and asking if there was something else that we could have done to make it more algebraic, if you will. And so you could add all this up and you're going to get 10n plus 45. And then you're going to need to multiply two of the numbers in it by 10. And then you need it to equal 100. So if I did these two, for instance, I would gain, they would become 28n, because you would have 2 10s and then 8 more n's. 28n, and I would gain 10 more on top of this, so it would be plus 55 is equal to 100. Well, when we subtract that, 45 is not a multiple of 100. So what if I switched to these two and tried to do it with that? So if I did it with that, I would actually have still 28n, because you're still doing 10n, 10n, and 8 more n's, but now you're gaining 27 on top of the original 45 you already had. Again, 27 because you're not gaining a full 10. You're gaining 10 and losing 1, gaining 20 and losing 2. So you'd be gaining 27, added on to this, what would that put you at? 60, 72. And if you look, that will be solved for n equals 1. And you could do it that way too. Feel free to explore it. Good question. It's kind of interesting. One last point to make, I forgot to mention at the beginning, it's a 60-minute test and the answers are all integers. That's it. On to the next question. All right, so continuing on. This is the Sigma Mathematics competition from August 2021. This was problem number 3. Find the sum of all positive integer values of n, so positive integer values for which that expression is an integer. I don't usually spend a lot of time with that. I'm just going to write n plus 6 over the square root of n minus 2 equals I. And certain things come to mind right away. Capital I for integer is what I use usually. It's just kind of a default mechanism. One thing I notice is that this is going to have to be a perfect square. So n minus 2 has to equal a perfect square. Perfect square. There's an R in there I couldn't fit. Okay. P-E-R-F. Okay, perfect square. And because if it's not, you're going to have an integer divided by, it's not going to be an integer, right? So then that's one thing I want to consider. Something else to consider is I don't really want the square root. I'd like to get rid of it. So I think what I'm going to do is square both sides. And if I do that, I'm going to generate n squared plus 12n plus 36 over n minus 2 has to equal an integer squared now, some integer squared. And this looks like, I obviously don't know it doesn't divide in, but I could do long division on it. Let's go ahead and do that and see what we generate. So n times what is n squared? I'm going to erase this. Just don't forget that n minus 2 is a perfect square. It's going to be times n. So n times n creates n squared. N times negative 2 is minus 2n. What you're going to do now for long division is subtract this expression from the top. But when you subtract it, you can basically change the signs. It's faster. And you make less mistakes when you change the signs and add rather than subtract. So add here, the first term will always go away, and if it doesn't, you made a mistake. 12n plus 2n is 14n, drop the 36. n times what is 14n? It's 14 goes there. I multiply to get 14n minus 28. Again, change the signs and add to get 64. This is your remainder. How do you know you're at your remainder? When the power of it is less than the power of the leading term, the degree rather. So we get that n plus 14 plus 64 over n minus 2 is equal to an integer squared. Keep in mind that n minus 2 has to be a perfect square. Okay, so if we already know that this is an integer, if this is going to be an integer squared, then this has to divide into 64. This gives us our options. We're going to have 1, 4, 16, and 64 as possible perfect squares to divide into 64. Again, if it doesn't divide in, you have a non-integer here and an integer here, the sum of which is never the square of an integer. So these are our possible values for n minus 2, and now we need to test them. So if n minus 2 is 1, then n is 3, and basically just add 2 to all of them. 3, 6, 18, and 66. The question is, do these actually work? You shouldn't be so confident just because you did some cool algebraic stuff and you feel so good about yourself. You should test them quickly to tell, because you're a human and humans make mistakes, and if you don't know that, you're going to make mistakes on the test and it's going to cost you. That goes for any competition, or maybe even in life. Okay, so what can we do? If we plug in 3 to here, I'm going to get 9 over 1. And of course, that's going to work. If I plug in 6, I'm going to get 12 over the square root of 4, which is 2. That's going to divide in, no problem. If I plug in 18, I get 16. And 18 plus 6 over 4, because you're square rooting 16, right? You're square rooting this number, right? That's going to be 4. This is definitely 24 over 4, which works no problem. What about 64? You square root it, you're going to get 8. And if I do 64 plus, oh, that one's not good. Oh, 66 is the actual n value. So 66 plus 6, careful, 66 plus 6 is 72 over the square root of 64, which is 8. All of these values of n work, and I know there are no more. Again, n has to be a perfect square divisor of 64. You can simply add these up in whatever way you would like. I will do, I don't know, 72 and 18 is 90, and add the 3 to get 93. We're on to the next problem. Okay, and so we're on to problem 4 from the Sigma Mathematics competition. Here we go. The sequence x1, x2, all the way to x sub 100 has terms that are all positive integers, and each term evenly divides the next term in the sequence. Well, I want to consider that probably later. X sub 100 is this expression. You've got 33 powers of 2, 3, and 5, all of them. Now, if half of the terms are divisible by 2, okay, so let's think about it. Let's say you've got some term x sub v, and it has a 2 to the, I don't know, third in it. okay, and it's got 3 to the b and 5 to the c. Then x sub v plus x sub v plus 1, the next term would have to have at least 3 powers of 2 in it. 2 to the 3 plus something times 3 to the b plus something times 5 to the c plus something. In other words, once you've hit your first power of 2, everything after has to have a 2 in it, and so would therefore be divisible by 2. So right away we can say if half of the terms are divisible by 2, and there's 100 terms, well then we cannot have our first power of 2 until the 51st one. So it would be x sub 50 would have to have at least 1 power of 2. So we'll put a here. And then we'll put a 3 to the b and a 5 to the c for now, where a is greater than or equal to 1, and also an integer. Okay? We're not proving it to someone, we don't need to explain all of that, but just for your understanding it has to be an integer as well. Okay, so if half the terms are divisible by 2, this way x sub 51 will also have at least 1 power of 2 in it. And then all the rest would then be, actually no, it's x sub 51 that has to have the power of 2. Let's change that. Good. And this would be 52 and so on. Almost messed that up. So that's because this first 50 terms start at 1, end at 50. That's the half. So this is the 51 through 100, the second half, all having at least 1 power of 2. Next up, 1/10 of the terms are divisible by 10. Well, to be divisible by 10, you got to have a 2 and a 5. We definitely got 2's all the way back from x sub 51. We need 10 terms to have a 5 in them, which means the first term that can have a 5 would be 91 all the way down to x to 100. This would have 2 to the a plus something times 3 to the something times 5 to the, this is the first time you could have at least 1 power of 5. So the first place you could have a 5 is here. The first place you could have a power of 2 is here. It doesn't have to be 1 as the issue. It could be 2 squared or something. If we just put a 1 to indicate that there couldn't have come before that, that's fine. That's not really what it means, but just think of it that way. Okay, so we gain our first 5 at x sub 91. Okay. Got it. And our first 2 here, which would mean there is no 5 here, and this c can just become a 0. We know there's no 5s. If there was a 5, it'd be divisible by 10, and that's not going to fly, because every number after it would be divisible by 10, because each term evenly divides the next term in the sequence. So next up, what is the minimum number of times some term, like v or k in this case, has to equal the next term in the sequence, meaning that they're equivalent, right? So let's think, obviously that must happen because, well, it's going to, right? Before this 50 right here, all terms x sub 1 to x sub 50 must have equaled 3 to some power. You would have to have 2 to the 0 and 5 to the 0 because they're not divisible by 2 or 5. Once you had a power of 5 there, it would have to stay the rest of the way, again, to meet this criteria. So again, we've covered that. I'm just refreshing, reminding, reinforcing the idea. So the next thing would be we can only have powers of 3 up to a max of 33. There'd be no reason to start at 3 to the 7th or something like that. We should make the first term x sub 1 could equal 3 to the 0. Has terms that are all positive integers. 1's a positive integer. That would work. That way we could go all the way to x sub 34 would be 3 to the 33. Because we added 33 terms, we'll add 33 powers of 3. So x sub 2 is 3 to the first. X sub 3 is 3 to the second, and so on, noticing that the subscript is 1 more than the exponent. We don't want to create any duplicates if possible, because we want to like minimum number of times some x. If I started, for instance, at 3 to the 33, like say my first term, x sub 0, 3 to the 33, that's going to create all the way to x sub 50. You'd have to always have that 3 to the 33 in it, which would mean you had the same one 50 terms. Or I'm sorry, x sub 1. 50 times. X you have 50 terms all with this, but that's not the minimum. That's more than the minimum. So we're avoiding that scenario by making it spread out. Okay, the next thing we have to do is continue on. X sub 35 to X sub 50 would all have to look exactly like this one. Okay, so because of that, we're going to have how many terms that look like that then? This is going to be 50 minus 34. Let's see. What is the minimum number of times some term x sub k has to equal the next term? 50 would not be included in that because it's not going to equal x sub 51. So we actually would probably want to stop at 49, and then it would be 34 to 49. Well, b minus a plus 1, 49 minus 34 is 15 plus 1. There will be 16 terms minimum between 1 and 50 that have the same numbers of 3. And you don't have to have them all at the end, but it doesn't really matter where you put them. It's going to come out the same either way. So the next thing would be, now what do we do? At x sub 51, we now have, let's say we start with 2 to the first, and we've got 3 to the 33rd, which it has to have, and 5 to the 0. Okay, so at this one we gain our first 2. The first time we gain a 5 is x sub 91. Now we'll have 2 to some power, 3 to the 33 for sure, and at least a power, 1 power of 5. Could be more, we don't know. But the nice thing is with 5 to the 33 all the way to x to the sub 100, you can split out the powers of 5 however you like, as long as it's increasing only. And there's plenty of ways to do that. So there's no duplicate terms between 91 and 100, which means any more duplicate terms, like same term in a row, would have to come between 51 and x sub 90. How many would there be? Again, this cannot be 2 to the 0, or it could be. No, it wouldn't. It has to be 2 to the first at least. Okay? And again, we'd like to spread them all out. So we're going to want 33 terms to have a power of 2. So I'm going to take 50 and add 33 to get x to the 83 should equal 2 to the 33 times 3 to the 33 times 5 to the 0. What that would mean is that from there until you get to x sub 90, they would all look the same. Just like we didn't include the 50 because it's not going to match 51, we are not going to include x sub 90. We're going to stop at x sub 89. All the terms from 83 to x sub 89 all have to have, or in my scenario, but you could have split it up differently, but you're still going to get a minimum of this, however you split it up. Okay? So 89 minus 83 is 6 plus 1. There's 7 more terms you're going to get from there. 7 and 16 total of Michael Jordan or LeBron James. Take your pick. It's 23, which is their jersey number. That's it. I think we're good here. I'm not sure if LeBron still wears 23. I can't remember. That's about all for that problem.